Okay. I am busy trying to open. No. Lectures. All right. Okay. So today we're actually going to work through friction factors for sphere packs. Laptop. There we go. So friction factors for sphere packs. We have last time introduced friction factor for a tube and for a sphere. Okay. The key idea is that friction factor will help me upscale regardless of my flow regime. And basically, we are ultimately looking for expression for friction factor that I can compute from measurable quantities. I typically go and look at the solutions for laminar flow that I actually have as analytical solutions in order to motivate myself what a good friction factor would be. And the key thing is that it has to be relatable to something that I can actually measure in the experiments. And then basically people go and collect a whole lot of experimental values for these friction factors and try to correlate them with Reynolds number. Okay? And from those correlations, we then take fits to those the experimental data as a predictive friction factor for all types of regimes. And of course, if I'm in a laminar flow and I have a tube, or I'm in a laminar flow and I flow around a sphere, I can actually find the analytical relationship between friction factor and Reynolds number, because for those, I actually have all of the possible things, velocity distribution, forces, and so forth that I need to evaluate. All of them I actually have ready to go, and I can plug in formulas. Okay. So now for friction, when I want to do the same thing for sphere packs, okay, of course I'm going to run into a little bit of trouble, because sphere pack in itself does not have a complete definition for flow in its geometry, not even in laminar case. We were able to upscale our reasoning and get an expression for permeability, for instance, for laminar case. Okay? So we will do a similar thing. We will basically try to go and find a relationship or find a good definition for my friction factor. And then again, you're going to measure a whole lot of friction factor in different sphere packs for different flow regimes and try to fit to experiments. And still, we will actually be able to find workable solutions. So let's do that. Basically, so I am trying to find or define what would be a good friction factor. And conceptually, okay, if I have flow around spheres, so I know I have some tortuous paths through this sphere pack, right? In our unit cell approach, we were actually looking at sort of sphere pack in itself, and we were packing a bunch of unit cells that were all spherical. Or in Karman-Kozeny approach, when we were upscaling, I was looking at some sort of average bundle of tubes, if you will, that I was going through. So basically, I have conceptually, I look at the flow through sphere pack either as flow around submerged objects, that is spheres, or flow through some average tubes. And this average tube, I have to figure out what it is, okay, for this particular porous medium. Flow through some tubes of some possibly complex cross-section. So those are sort of two concepts that we're actually using to upscale flow through sphere packs, because ultimately I don't know all of the details of the geometry. Okay. And here in friction factors for spheres, we're going to kind of combine both, possibly in a slightly odd way, but it's simply ultimate test is, even if you do a little bit of magic to come up with a good definition for friction factor, your ultimate test is, okay, great. Once I compute these friction factors for experimental measurements, does a good correlation jump out of them? Okay, and if it does, then you actually made pretty good assumptions. Okay, so let's do that. My first step is will be okay. This is basically using this view that I'm flowing through some sort of average type of tubes. I'm going to define friction factor for a bed. I'm going to call it F bed. I'm going to define inspired by fanning factor for flow in the tube. But wherever in fanning factor I had something that was related to a tube, I attempt to translate that to something that I can say about the sphere pack. So basically I'm going to define it as 1/4 diameter. This was diameter of a tube, but here it will become diameter of my particles in this bed. And is it exactly true? No, it's not. But I know that those two diameters, even if I have this some magical average tube going through a sphere pack, diameter or some sort of average cross-section of that flow path, it has to be correlated to diameter of these particles, okay? Is it maybe 1/5 of it or 1/6 of it or some sort of fraction, but it's definitely correlated. So it should up to some constant that I can fiddle later and sort of like fit it to my experiments. Up to a constant, this should be okay. So dP divided by length of this sphere pack. And then pressure difference over 1/2 rho. And here I had average velocity through the tube, but I don't have that for sphere pack. So what I will put is V0, and V0 will be Darcy velocity, because that's something I can measure. It's my volumetric flux divided by area. And dP is particle diameter. So again, I replaced tube parameters with something similar for a sphere pack. And again, if I'm looking at this average sphere, average flow path, even if I don't know what's average velocity through it, okay, it has to be somehow related to the Darcy velocity going through. Otherwise, this is not my average tube that is going through my sphere path. Okay, so that should work. So replacing average VZ with V0 should work. Pressure gradient is pressure gradient, and dP, so diameter of this imaginary average tube going through should be related to the particle diameter. Okay, great. Now, these are some of these average tubes. So if I actually had a tube, okay, then I can actually see what the flow through that tube should be and what the friction factor should be for just an individual tube based on our definitions. So second thing I will do, okay, I will look into an average or representative tube through the sphere pack. Okay. And I'm going to say, okay, R is this tube radius. And if I attempt to relate it to the sphere pack, we're used to using hydraulic radius concept. So it should be equal to 2RH, where RH is hydraulic radius. And if V0 is the Darcy velocity that I actually measure for the entire sphere pack, okay, and phi is the porosity of my entire sphere pack, how is the average velocity through this tube related to Darcy velocity? What I call interstitial velocity. Divided. So basically my average velocity is V0 divided by phi, where phi is porosity. So this is interstitial. And it makes sense, right? If I'm measuring Darcy, I'm always measuring, dividing by the area of the entire sphere packing, regardless of what the porosity is in there. So if I'm thinking, if I'm looking at some average flux through that, well, I kind of, if I'm going through some tubes inside that packing, I gotta go faster. So basically, I will get a faster velocity, faster interstitial velocity when I divide by phi. Okay. So for one tube, this friction factor for this average or representative tube is my, by definition, Fk divided by Ak, where Fk is my kinetic force, and we said that in a tube that is equal to this dynamic part of drag force on the walls is balanced by pressure. So it's pressure difference times the area it's acting on, right? So this is from that macroscopic balance, but we could also just integrate tau RZ. And then define my area as 2 RPL and 1/2 rho square. So since RH is R over 2, I can write this as P0 minus PL divided by 1/2 rho V square RH over L. So I'm just actually curious here for two things. I would like to actually relate now this friction factor for the bed, which I kind of just threw on the page. Okay, this is what I can compute from the flow parameters for the sphere pack. And let's actually relate the two, and we can also plug in what RH means in terms of porosity, volume, and specific areas in this sphere pack. And let's see how, where I get in terms of the relationship of the two. Okay. And I'm going to open another page. So I'm essentially trying to figure out, well, what is this F bed? I kind of just threw it. I can compute it. I don't know how it's really related to anything that I have in this sphere pack. So I'm going to relate these two definitions of F bed and F tube. So basically, my step 3 is relate F bed and F tube. And one thing that is common in both, that is definitely true for both, is this pressure difference. So I can actually eliminate pressure difference, or expressing it from both of the equations. So basically, P0 minus PL is, in terms of F tube, 1 rho V square L over R H F tube. And this part is actually my V0 square over phi square. So I can plug into F bed. And that's just a little bit of algebra, dot, dot, dot. F bed as 1 over 4 phi square dp over RH F tube. Another step here is I know that hydraulic radius, I can actually find it for sphere pack. That's something that we did in Karman-Kozeny derivation. So this RH was equal to basically cross-sectional areas open to the flow, okay, divided by the vetted perimeter, which when I actually scale up to the volume, it's going to be void volume divided by the total vetted surface. Okay, so it's void volume in sphere pack divided by the total vetted surface. So it's porosity times volume divided by my specific area times volume. Just as a reminder. And specific area, S, was recalled from sphere packs and Karman-Kozeny. It was, I'm just going to throw it on the paper, it was 6 over dp times 1 minus p. So once we plug all of that in, I'm going to get a final relationship, F bed Okay, so basically this definition for my friction factor for a bed that I basically threw down on the paper based on stuff that I can measure for this flow seems to be related like this to this average friction factor for a tube. And this is actually where we actually come in, and we're going to do, well, we're going to watch that on a video. But essentially what you now come in and do, say, okay, for different flow regimes, I know what expressions for F cube should be. Okay. And basically for different flow regimes, you're going to get different relationships for this fanning factor. So now what basically remains to be done is substitute different flow regimes. Okay. And of course, compare and fix as necessary compare with experiments and fix as necessary. And we will actually ultimately, from these measurements of F bed and relating them to the Reynolds number, get different relationships. Ultimately, they're typically expressed for pressure drop. In laminar flow regime, that relationship would be very similar to, but not the same, to Carman-Kozeny, and it's going to be called Blake-Kozeny. And then we will have, hi, that's the test.
This is a test of the emergency warning
End of class.
system. This is only a test.